So folks, today we're going to go over the 50s, but we're going to start with some initial information. So my first question is, what does co actually mean? So try to think of some words that start with co. So we got the words co-pilot. What does that mean? Well, that means another pilot that you fly with. Cohabitate, that means to habitate or to live with someone else. Co-worker, someone you work with. Covalent, that's a chemistry term. So in all these, you're sharing some kind of duty, sharing something. And we're going to share valent or valences. So here we have carbon dioxide. And if we look at carbon dioxide, we have an oxygen on each side, a carbon in the center. We have the innermost electron shells of all three elements filled. And then we go to the outermost shell. And remember that earlier we were taught in every shell but the first one, we want 8 electrons. Well, oxygen's got 1, 2, 3, 4, 5, and 6 electrons in its outermost shell. And that's the same thing for the oxygen. So oxygen needs to get 2 more electrons. And what it does is it shares some electrons with carbon, and carbon shares some of its electrons back. So if we look here in this instance, carbon is sharing this electron right there and this electron right there, giving oxygen 8 electrons. And the same thing's happening on the other side. Carbon is sharing that electron and that electron with oxygen, and this oxygen now has 8 electrons on its outside. But carbon gets something out of it as well. This oxygen is sharing that electron with carbon and that electron with carbon, bringing it up to 6 electrons in its outermost shell. And this oxygen is sharing that electron and that electron. Now carbon has 8 electrons in its outermost shell. All of these electrons being 8 in the outermost shell are all a result of sharing electrons. And this is what we call covalent compounds. So covalent compounds, we share electrons to become more stable. Covalent compounds are all nonmetals. You might want to pause the video, grab your periodic table, maybe right above the chunk that's nonmetals, and maybe you could write the words covalent compound and say when nonmetals react or nonmetals form compounds. So here's water, a very stable compound. Water's not exciting. It does some neat things, but it's not really considered an exciting element. So here we have hydrogen with 1 electron in its innermost shell. And remember, the innermost shell of every element can only hold 2 electrons. So what does it want? It wants 1 more electron. And the same thing with this hydrogen down here. It's got 1 electron in its outermost shell. We look at oxygen over here. It's got 1, 2, 3, 4, 5, 6 electrons in its outermost shell, and it wants to get 8. So again, innermost shell, 2 electrons, outermost shell, it wants 8 electrons. So what happens is this hydrogen shares an electron with the oxygen. This oxygen shares electrons with the hydrogen. Now hydrogen has 2 electrons. And oxygen would have 7, but the same thing happens with another hydrogen. This electron is shared with the oxygen. This electron is shared with the hydrogen. And now we have 2 electrons in the outermost shells on those, and we have 8 electrons in the outermost shell of the oxygen. And now we have water. So again, water is a very stable compound. It doesn't start on fire, doesn't give off light, doesn't make loud sounds. It's a very stable compound. It's all because 2 electrons in that shell, 2 electrons in that shell, and 8 electrons in that shell. So full shells give you very stable compounds. Ionic compounds, that's everything that we talked about earlier when we started naming compounds. So the other 4 cases are all ionic compounds. That's when a metal and a nonmetal react, or a metal and a polyatomic ion. And those polyatomic ions are found on the back of your periodic table. And when you have an ion in a compound, it is definitely ionic. You might want to write this on your periodic table, ionic compounds. So in ionic compounds, no sharing occurs. We talked about this here. We have sodium, it's got one lonely electron on the outside. We have chlorine in its outermost shell, it's got 7 electrons. So sodium donates or gives up that electron to chlorine, and now sodium's got a positive charge and chloride has a negative charge. They're attracted to each other, but this positive charge and negative charge, those are ions. When you gain electrons, you become an ion. When you lose electrons, you can become an ion. So if you don't have the same number of protons equaling electrons, you have ions. And if you have ions, you have an ionic compound. Is this ionic or covalent? Pause the video. Take a guess if you have to. This is a covalent compound because they're sharing electrons to get their shells full of electrons. So let's start a new case. This is where your 50s come in. So we look at this reaction. This reaction is called the photosynthesis reaction. Water combined with, what's that called? Makes glucose and oxygen. What is that called? Do you know what that's called? It's the stuff we breathe out. What do you call it? Well, if you called it carbon, because there's carbon there, and you called it di, because di means two in Greek, di, and then you didn't call it oxygen, but you called it oxide, carbon dioxide. If you already knew that, you know how to name these kinds of compounds. Notice we don't put any Greek prefix out on the front if the first element is a single element. We'll talk more about that as we're going along. So up here, case E, all the compounds are found in the nonmetal section. That's this triangle right here. You have nonmetals written right there at the top of your periodic table. So everything's found in this triangle. These compounds are covalent, meaning they share electrons. We don't look at charges. We don't care about the charges that are in each of these boxes. Doesn't matter. They're all negatives. Negatives can't add up to 0. We're going to look at subscripts. Now, H2O, that too is called a subscript. It's below the other things there, sub, below. We're going to convert those subscripts to Greek prefixes. On the back of your periodic table, this chunk of information is right here. So we give you the Greek prefixes right below the Roman numerals, and we're going to use those Greek prefixes. Don't worry, you always get to use your periodic table on all quizzes and tests. So you don't have to memorize the Greek prefixes, but you will come to know them. It says write the name of the first element as is, unless there's more than one of that element. Write the second element, add a Greek prefix if to it, and then the ending name of that first one. So it gives you 2 examples. NO2, nitrogen dioxide. So there's only one N in nitrogen dioxide, so it's NO2. NO2, so we just named the first element as it is, nitrogen. And now how many oxygens are there? There's 2 of them. So we go down here. 2 is the Greek prefix. We need to use di, and then we change oxygen to oxide. The next one is N2O4. So right here, I'm going over this example, N2O4. Now there's more than one of the first element. So again, we use di. So we go di, meaning 2. 2 what? 2 nitrogen. And now we have 4 of the oxygen. 4 is tetra. So I'd write this all in one line if I could, but I ran out of room. Tetra oxide. Change that last element, chop off the last part of the name, and I. So let's do some of these problems. So here we go. We already did this one. There's 1 carbon. If there's only one of the first element, we don't use a Greek prefix. So carbon. And we have 2 oxygens. Di is the Greek prefix for 2. And not oxygen, but oxide, dioxide. These double vowels, you'll have to decide when to use them and when not. You just kind of have to say it out loud. And if it sounds stupid, you probably don't need a double vowel. If it sounds stupid without a double vowel, then you have to include that. And you'll get the gist of it as you move throughout chemistry. So what's this one called? It's the stuff you breathe in that kills you. It's called the silent killer. It's found in cigarettes. If your furnace in your house goes bad, it might be pumping out a lot of this chemical, which could kill you. So there's only one of the first element, so carbon. And there's only one of the second element. And here we use a Greek prefix. So mono is what one means. And then oxide. Now, if I said carbon monoxide, that sounds kind of stupid. So what I do is I get rid of the double vowel and I go carbon monoxide. And that is the name. Again, you just kind of have to listen to it until you get the knack of it. I would like you to try these next two. So pause the video, try these next two, and then I will go over them. Well, I'm hoping you pause the video. Pausing the video and trying these problems, that's the true way to learn rather than just watching through it. So here I have 5, and if I go to the Greek prefix list on the back of your periodic table, we find out that 5 is penta. Penta what? Well, 5 of what? 5 nitrogens. So pentanitrogen. And now we have 3. The Greek prefix for 3 is tri. Again, right off the back of the periodic table. And 3 what? Not 3 bromines, but 3 bromides. Tribromide. Let's do this one up here. We have 1 sulfur, so we just write sulfur. Common mistake, a lot of people will go with an ER on that one. It's a U. And now we have 6 of these fluorines or fluorides. So hexa means 6 in Greek. And this is another very misspelled word. F-L-U-O-R-I-D-E. A lot of people want to put the O first, but that would be called flouride, like the white powder they make bread out of. So those are the names for that one. Again, pause the video and try this next one if you haven't already. So here I have 2 nitrogens, so 2 dinitrogen. And I have 1 oxygen, monoxide or monoxide. This one we save for its own slide because it's very interesting. Let's name it first and then we'll talk about it. So 1 nitrogen, so that's just nitrogen. We don't put mono on the first element if there's only one of the first element. But we have 3 iodides, so triiodide. If I called it triiodide, that wouldn't sound as good as triiodide, so that's why there is a double vowel there. So if we look right here, these are the outermost rings of each of these elements. We see it that they are covalently bonding. They are sharing electrons here. But if you grab your periodic table and you look at element 53 and how far down it is on the periodic table, that's iodine, it is a massive element. And it's got a lot of electrons. And those electrons all have negative charges. And those negative charges want to get away from each other. So what happens is this element or this compound is made, but these electrons want to get away from each other so bad that if you touch this element, it explodes. So we're going to watch a quick video of this material exploding. So are all of you screaming at home as well? I doubt it. All right. A couple questions before we get to the homework. It says circle all the definitions that explain what an ionic compound is. Ionic, that's a lefty and a righty, a metal and a non-metal on the periodic table. When I say lefties, I mean metals. When I say righties, I mean non-metals. So a non-metal reacting with a non-metal. No, that's not an ionic compound. A metal reacting with a non-metal reacting with a non-metal. That is an ionic compound. Metals have positive charges when they lose electrons. That's the definition of a metal. Elements that want to lose electrons become positively charged. And non-metals, they want to take on electrons and they become negatively charged. A metal reacting with a polyatomic ion. That's an ionic compound. Ammonium is NH4 1 positive. It's the top one on the back of your periodic table for polyatomic ions. So a polyatomic ion reacting with an polyatomic ion. So anytime polyatomic ions involved, it's an ionic compound. The word ion clues you into that. One element loses an electron while another gains an electron. Well, we talked about that with sodium and chlorine. The sodium gives up an electron, becomes positively charged. The chlorine takes on an electron, becomes negatively charged. So when you lose electrons and gain the same electron, that is an ionic compound. And F2 elements sharing electrons to attain full shells of electrons, that's not one. So we have the exact same setup down here, except for here we're talking about covalent compounds. So nonmetals reacting with nonmetals, and two elements sharing electrons to get full outer shells. Those are the two definitions of covalent compounds. So 50.1 is your homework. It's a mixture of all 5 cases that we have discussed so far. So the first thing you need to do is look at the information and try to figure out what case it actually is. So on your cover, we have this information, and I'll show you that on the next slide. So as you're going through the information, you can ask yourself, if there's more than 2 elements in the compound, it means you have a polyatomic ion on your hands. So that means you're going to be using the back of your periodic table. If the first element is a metal with multiple charges, that means you're going to need a Roman numeral in parentheses. You're going to have an ending with I. If the first element's a metal and it only has a single charge, you don't use any Roman numerals and you don't use a parentheses. 4, if the first element's a non-metal, 95% of the time you're going to be using Greek prefixes because you have a covalent compound on your hands. There is an exception when you have 2 polyatomic ions. So that would be the ammonium ion with some other polyatomic ion. So again, this is your cover. These steps are right here. You might want to use those as you're going through, but it's those 5 different types of naming compounds that we taught you so far. You just have to decide which rules you need to use for each setup. Have a good day, and feel free to contact us if you need any assistance.